So finally, I want to talk about some of the geometry of gradients and directional derivatives. So recall my directional derivative in the direction u of f of ab, so my function f at some point ab, we just define that to be the gradient of f evaluated at ab dotted with our unit vector, whatever that unit vector might be. And recall from our definition of dot products that this is exactly equal to the magnitude of the gradient of f at AB times the magnitude of my unit vector u times the cosine of the angle between them. We're going to use this identity to explore what this looks like using some contour plots and specific examples. So let's look at a specific contour plot given by the function. Here's my example. My function f of xy, we're going to continue exploring the function x squared minus y squared. And looking at this contour plot, we notice that when my x's are exactly equal to my y's, that's when I have contour lines that are equal to 0. So here's my x and my y, and this is a contour line where z is equal to 0. When z is equal to 1, I have 1 equals x squared minus y squared. That's going to be a hyperbola, and that hyperbola is given by, if I notice my x value being equal to 1, that's going to be a point on this hyperbola where y is 0. And in general, my contour plot is going to be a bunch of these hyperbolas. I'm not going to draw them all, but it gives us an idea of what this plot looks like. So let's say I wanted to evaluate the directional derivative in the direction of, let's say, this direction. I should use a red vector. So this is the directional derivative. I want to know, whoops, what is the directional derivative where my u vector is equal to the vector where my x's are increasing by 1 and my y's are increasing by 0. I know this is 1 unit in length because of the way that I defined this vector, and I'm going to evaluate it at the point over 1, 0. That's just a coincidence that I decided to put it at this point facing in this direction. And when I evaluate this, what did this give me? First I have to compute the gradient of f evaluated at the point 1, 0, and then I'm going to dot it with my vector 1, 0. The gradient of this function, as we said before, is just the vector 2 times x, which is 1, minus 2y, which is 0, dotted with, 2 times x is 2, dotted with 0 plugged in for y gives me 0, dotted with my vector 1, 0, and it gives me some output. In this case, 2 times 1 plus 0 times 0 gives me an output of 2. So I just found that the directional derivative of this function evaluated at the point 1, 0, where my direction vector was given by the direction vector 1, 0, I get a directional derivative of 2. Well, what exactly does that mean? This is only meaningful when it's evaluated relative to other points. So stepping away from the actual numbers, let's look at our definition of dot product and see what that means for directional derivatives. So for example, we know that our directional derivative is given by the magnitude of each of these two pieces times the cosine of the angle between them. Well, at any given fixed point, let's go ahead and fix ourselves at some point out here, AB. Once I've fixed myself at the point AB, I know that the magnitude of the gradient evaluated at that point is always going to be whatever it is. This isn't going to change. And my magnitude of u, my directional derivative, is always equal to 1 because we're choosing our u to be a unit vector. So really the thing that can change is the angle between this gradient and this cosine of theta. And it turns out that what are the values that cosine of theta can be? That this whole directional derivative can be equal to 0 when the cosine of theta is equal to 0. Let's recall that the cosine of theta is equal to 0 when my theta is equal to pi over 2, right? That's a 90-degree angle. That's when my cosine is equal to 0. And my cosine is equal to 1 when my angle theta is equal to 0. Obviously, these are only certain examples. It's a whole circle, and so it goes around and around. But for the sake of clarification, that means that when the unit vector is perpendicular to the gradient, that's when my directional derivative is 0. So I'll write that down. When my unit vector is perpendicular to the gradient function, then my directional derivative is 0. Excuse me. My directional Let's take a look of what that means here on this graph. If I represent my gradient, we just found out that if I decide to step perpendicular to my gradient, then I'm not going to have any change in elevation. So that's saying that as I walk along a contour plot, my gradient is going to be exactly perpendicular to that. So that's also exactly saying, so this is another way of saying that gradients are perpendicular. I should probably use the word orthogonal to level curves. Because my derivative is 0, there's exactly no change in my z value when I walk along my level curve. And that happens exactly when my unit vector is pointing perpendicular to my gradient. So this is two ways to say the same conclusion. And that happens when my cosine of theta was equal to 0. Let's explore the second possibility. Let's suppose that my cosine of theta is equal to 1. I'll write these conclusions in green. So if my cosine of theta is equal to 1, that means that my directional derivative, so when my directional derivative u is parallel to the gradient, then the directional derivative is maximized. What do I mean by maximized? I mean that the outputs of my directional derivative, these two things stay fixed. And so the only thing that changes is that angle between them. So as my directional derivative spins around in circles, my outputs for the directional derivative, when my direction vector spins in circles, the directional derivatives that I get out can vary in values. And we find out that those values are highest when I'm traveling in the same direction as the gradient. In other words, when I travel in the same direction as the gradient function, that's my direction of greatest change. So let's write that conclusion down below here. That's saying that the gradient is the direction of greatest change. So previously we had talked about paths of steepest descent. If I start at some point AB and I want to know what is my path of steepest descent, the path of steepest descent is to always go perpendicular to the level curves. That's something that we talked about before. And at any given point along here, that path of steepest descent is going to be following along exactly what the gradient measures. So the gradient measures the direction of steepest ascent. That's exactly what we found out by analyzing the geometry of these directional derivatives. So there are two conclusions here. One conclusion is that the gradient is the direction of greatest change, and another conclusion is that gradients are always perpendicular to level curves. So next, we're going to finish up with talking about gradients and level surfaces. Let's say that I have a function that's a three-variable function. F of x, y, z is given by x squared plus y squared plus z squared. Now, the gradient of this function is going to be the partial derivative with respect to x, which is 2x for the x component. The partial derivative of this with respect to y is 2y, and the partial derivative with respect to z is 2z, because all of the other components drop out when you take the partial derivative with respect to z. We treat these as constants. The derivative of a constant is 0. So the reason why this is interesting, we just saw that gradient functions are always going to point in the direction that is perpendicular or orthogonal to level curves. Here we're going to see an application where gradients are always going to be orthogonal to level surfaces. And I'll write that down. Gradients are orthogonal to level surfaces. So let's recall the geometry of level surfaces. Level curves, we said our outputs are z values equal to a constant, and that gave us this nice shaped curves. We're going to do the same thing here, only this time our outputs are a fourth variable. So let's look at the level surface given by, let's say, 4 is equal to x squared plus y squared plus z squared. Notice that this level surface is a sphere. It's a sphere with radius square root 4, which means that it's a sphere of radius 2. This is one particular level surface, and if I were to plot all of the level surfaces for this function, you would get a set of ascending spheres, right? That it would be like dolls nested within one another, a sphere within a sphere within a sphere within a sphere. I'm not going to draw all those level surfaces because it would look really messy, but our gradient, the three-dimensional analog here is telling us that when I compute the gradient at a fixed point, let's consider the gradient of f evaluated at the point 1, 1, 1, that's going to give us the vector 2, 2, 2. Notice that in the surface, I'm going to go, oh, 1, 1, 1 doesn't live on this surface. I'm sorry, this was a really bad example. So I'm going to go back, because we want to look at a gradient that lives on this particular surface. So we have to pick a point that lives on this surface. This is a good mistake to make for you guys. So what's a point that lives on this surface? I know that the point 2, 0, 0 lives on this surface, because when I plug it in, it satisfies the equation x squared plus y squared plus z squared equals 4. So now when I'm looking at the gradient of f evaluated at something that actually is on this surface, that's going to give me out a gradient function for, or a gradient vector for 0, 0. So what is this telling me? This tells me that when I'm at this point where x equals 2 on the surface of the sphere, I'm going to have a gradient vector that's given with an x component of 4 and 0 for the other components. So this is the vector 4, 0, 0. And notice that in this picture it makes sense. It looks like this gradient vector is pointing exactly outwards from the sphere. And it's always the case that the gradient vectors are going to be orthogonal to these level surfaces. So if I picked any other point and plugged it into this function, it would give me a different normal vector. Why is this interesting? As you'll explore in your homework, you can use this information to be able to come up with tangent planes. That this is the normal vector to the tangent plane at this point. So we covered a lot of stuff today, and I realize it was a big day, but I think this is pretty cool stuff. We talked about computing directional derivatives, derivatives of compositions of paths with functions. We also talked about computing directional derivatives and the geometry of gradients and directional derivatives.